I am Seema and welcome to part 3 of the chapter Electrochemistry. In the previous video, I explained the electrode potential to you. That if you take a salt solution and you dip a metallic rod into it, which is going to act as 1/2 cell, the electrode which is dipped into the solution, the metallic rod, there are two opposing processes that are occurring around it. One, the metallic ion which is present inside the solution has a tendency to get collected around the electrode, rendering it positively charged. At the same time, the metal atoms inside the electrode have a tendency to lose electrons and enter the solution in the form of the metallic ion, leaving the electrons in the rod, therefore making the rod negatively charged. Now, whichever process is stronger at equilibrium, that is the charge that the electrode would have. Thus, a separation of charges that is created would give a potential to the electrode. Also, I told you that if the solution here is present is a 1 molar unimolar solution, or if your electrode was not a solid metal, it was, let us say, a gas or a liquid. If it was a gas under standard conditions, a gas under standard conditions would be at 1 bar, and the temperature would be 298 Kelvin. Under these conditions and the solution, the concentration of the ions in the solution should also be 1 molar. Under these conditions, which are standard conditions, the potential of the electrode would be known as the standard electrode potential. Now, in this video, we are going to study how do we measure the electrode potential. There is a problem with measurement of electrode potential. You can never measure the electrode potential of one electrode. You always measure the potential difference between two electrodes. All you can do is you can measure that this one and this is the difference in their energies. For example, I'm standing here, you don't know how much energy I have. And you are standing here, I don't know how much energy you have. We decide to have a tug of war. We start pulling at a rope. Now, whichever is stronger would automatically be pulled towards the other. So, we do not know which out of us is stronger unless we have the tug of war and we see the difference, that at what speed did let us say you were stronger, at what speed did I move towards you, or how quickly were you able to defeat me at the game. So when you have two electrodes, you do not know the individual electrode potentials of them, but only the electrode, the difference, the potential difference, which is known as the E.m.f of the cell, of the electrochemical cell, can be calculated. Therefore, measuring electrode potential, single electrode potentials, was not possible. So we had to work around this situation. And how was that done? That we gave a reference. We made something a reference. And that something that we made as the reference electrode was known as the hydrogen electrode. And the conditions were standard conditions. Therefore, we called it the standard hydrogen electrode. Now, what does the standard hydrogen electrode consist of? What is it and what is its E.m.f? The standard hydrogen electrode is actually a platinum, finely divided platinum, which has been put over platinum foil. And platinum, as you know, is an inert metal. So platinum is not really the electrode. As the name suggests, it is the hydrogen electrode. And hydrogen is a gas. So you cannot have an electrode, it's not a metallic rod that can be dipped. So the surface which is provided, or the base for the electrode, is that platinum. And why do we take platinum? Because we do not want platinum to be acting in the process. We do not want it reacting. We want hydrogen to be oxidized or reduced so that we can calculate its electrode potential. So platinum, which has been coated with platinum black, which is just a powdered form of platinum, but which is inert. We take that inert electrode and there's a test tube, and in the test tube we bubble hydrogen gas through it. And since we call it the standard hydrogen electrode, this gas that is bubbled through it should be under standard conditions. That is, it should be 1 bar. And the solution which is present, which is an acidic solution, should be a molar solution, 1 molar. Its concentration should be 1 mole per liter. So when you have these standard conditions, under these conditions, the electrode potential would be known as the standard hydrogen potential or electrode potential. Now, as I told you that we used this as a reference. So we don't know what is the value of an individual electrode potential. We just assigned it a value. And it is always easiest to assign a value which is 0, because anything higher than that would be a positive value and anything lower than that would be a negative value. So it becomes easier numerically to compare it. So the value of 0 was assigned to the standard hydrogen electrode. Now the question is, okay, it was assigned, but how was it even measured? How did you verify it that the standard hydrogen electrode potential was 0? Simple, we assigned a value. So if you had two hydrogen electrodes, one acting as an anode and the other acting as a cathode, and you compared their electrode potentials, what would it be? What would the difference be? The EMF of such a cell be? It would be 0. Right? The EMF of such a cell would be 0, which confirmed, and when you calculate the EMF, it turns out to be 0 and has to be logically when you're using the same electrode as anode and cathode. Obviously, the electrode potential would be 0. That was done. And how do you represent this electrode? Platinum solid, which acts as a base, is written. You put a slash, and hydrogen gas is the one that actually acts as the electrode. And along with its reduced or oxidized form, both the oxidized and reduced forms of the electrode are written. So you have H2 gas and H positive aqueous. What is the reaction that is taking place when you use the standard hydrogen electrode? Since we always talk of reduction potentials, we'll talk of the reduction of hydrogen ion. So H positive ion, which is present in the solution, it gains an electron and results in the formation of hydrogen, which is present as a gas. That is half molecule or mole of hydrogen gas. Now I have explained what the standard hydrogen electrode is here. It is a platinum electrode which is coated with platinum black, and it is dipped in an acidic solution, and pure hydrogen gas is bubbled through it. And it is this pure hydrogen gas which is the actual electrode. The platinum is only a surface, it is like a catalyst, it is giving you a platform to act on. The concentration of the reduced and the oxidized forms of hydrogen is 1. Why? Because we are talking of the standard conditions. And since hydrogen is a gas, the pressure of this gas should be 1 bar and the temperature of this reaction should be 298 Kelvin. Under these conditions, the potential assigned to the standard hydrogen electrode was 0. And when we made an electrochemical cell where we had the anode and the cathode, both the standard hydrogen electrodes, and you calculate the EMF of the cell, E0 right, which talks of cathode, minus E0 left. Let us say the one that we had measured, we had assigned the value of 0, we make it the anode. So minus EL0 would become 0 because that is the value we've assigned. So EMF of the cell would be equal to ER, whatever is the EMF of the right hand side, that is the cathode. And in the case of hydrogen, if you take both of them as hydrogen, the EMF of the cell would come out to be 0. Because both of them, ER and EL, both are 0. But why do we write this here? Because if you take any other metal as the cathode and you take hydrogen, the standard hydrogen electrode acting as the anode, now reduction always occurs at the cathode. So you put it on that side and you calculate the reduction potential or the EMF of the cell under such conditions. Whatever is the EMF is the reduction potential of that other electrode. And in reference to hydrogen, which has been given a value of 0. So now that helps you to know, you take different metals and you find if the electrode potential of hydrogen is 0, and you make a cathode of copper, you make a cathode of zinc, you make a cathode of whatever metal, that whatever is the EMF of the cell would be the electrode potential of that other half or of that other electrode. So that is how the EMF of the cell gave you an idea of the electrode potential. So let us take one example. We take the example of the Daniell cell. As I told you yesterday, that when we represent the electrode or when we represent a cell, we always write the anode on the left and the cathode to the right. So when we are writing down the representation for such a cell, the anode is the hydrogen, the standard hydrogen electrode. So we'll first write that is platinum solid with hydrogen gas at 1 bar and H positive, that is aqueous and 1 molar solution. So we have shown the 1 bar and 1 molar solution, and of course we will assume that the temperature is 298 Kelvin, so it is the standard hydrogen electrode. So the electrode potential that you would get would also of the other electrode, if you have 1 molar solution of that also, you will get the standard electrode potential of that other metal. So we take copper in this case, copper ions, let us say it is copper sulfate solution, it is an aqueous solution and the concentration of that solution is 1 molar and solid copper. So this would, when you calculate the E.m.f. of this cell under these conditions, you will get the standard electrode potential. You will actually get the E.m.f. of the cell. But since the electrode potential of hydrogen is 0, therefore whatever is the E.m.f. of the cell is actually the electrode potential of the copper electrode. And when you calculate this, we find that the electrode potential or the E.m.f. of this cell comes out to be positive 0.34 volts. Or we could say this is nothing but the electrode potential of the half cell, which is, it is being contributed by this half because that other half has a potential of 0. So for this half cell of the reaction, what is the reaction that is occurring? Reduction is occurring. Therefore, CO2 positive aqueous 1 molar plus 2 electrons to give you copper solid. So reduction of copper ions is occurring in 1 molar solution and its electrode potential has been calculated to be positive 0.34 volts. What does this indicate? Hydrogen, if it is present, now if there is a competition between hydrogen ions and copper ions have a positive reduction electrode potential, which means in comparison to hydrogen, copper has a tendency to get reduced, or copper acts as an oxidizing agent for hydrogen and it itself gets reduced. Therefore, hydrogen cannot oxidize copper while copper can oxidize hydrogen. What does this signify? That copper does not dissolve in an acidic solution. Why? Because in an acidic solution, H positive ions are present and the tendency of copper is to stay reduced and not oxidized. In order to displace hydrogen ions, copper will have to get oxidized. It will have to lose 2 electrons and those 2 electrons will have to be taken up by hydrogen. But since hydrogen does not have a tendency to get reduced, rather, it is copper which has a tendency to get reduced. Therefore, copper cannot displace hydrogen from the acidic solution. So, copper cannot dissolve in hydrochloric acid. What does this signify? What does this tell us? That if you take a copper vessel, you can put a mildly acidic substance into it. You can store an acidic substance in a copper vessel because the copper vessel will not be affected by the presence of the acid. But it has been noticed, if you put nitric acid in a copper vessel, the copper vessel develops holes in it and instead of getting reduced, the copper gets oxidized. Now, how does the logic work here? This process actually occurs not because of the hydrogen which is acting as the electrode, but in nitric acid, the nitrate ion is the one that oxidizes hydrogen. Therefore, this is an exception. In the case of copper, you can store acids which have H positive ion only responsible for the acidic character. But in HNO3, the nitrate ion also has a tendency to oxidize it. Therefore, you cannot use a copper vessel to store nitric acid. This can come as a question. Let us move ahead now. So this was 1/2 of a Daniell cell where we took the copper electrode and we found out its electrode potential to be 0.34 volts and what does it mean in terms of the hydrogen. Now similarly we take the zinc electrode now and we calculate its E.m.f. in comparison to the hydrogen electrode. So the similar process we carry out, platinum solid is the surface, hydrogen is the electrode, which is a gas at 1 bar. It means standard hydrogen electrode, H positive, aqueous solution 1 molar. So we are talking of standard conditions, and it is the hydrogen electrode which has a value of 0. And along the salt bridge, you have zinc ions. So on the right hand side, you have the reduction occurring, and on this side, this is the anode, and that is the cathode. Oxidation occurring, oxidation half, reduction half. So zinc ions, which is aqueous 1 molar, and zinc, again standard conditions. And when we calculate the electrode, the EMF of this cell turns out to be minus 0.76 volts. Which, since the electrode potential of hydrogen is 0, it means this value is who is responsible for this value? Only the zinc half. The other half, that is the cathode half of the cell, is responsible for this electrode potential. And since it has a negative value, what does it mean? A negative value of zinc means that zinc does not get reduced. This has a tendency, so much of negative tendency to get reduced, rather this much of tendency, positive tendency, it has to get oxidized. So it has a stronger tendency to get oxidized in comparison to hydrogen. So if you have hydrogen ions and zinc metal, the zinc metal will lose its electrons and get oxidized, and the hydrogen which is present will get reduced, and therefore the zinc metal rod, it will start tarnishing, it will start melting away. And it will start melting away because the zinc has a stronger tendency to get oxidized in comparison to hydrogen. Therefore, now if this is the voltage of the EMF of the cell, and we want to create a Daniell cell, what do? We have two halves. We have the copper half and we have the zinc half. Now, which out of these logically do you think is going to act as the anode and which is going to act as the cathode? Based on the potential difference, we know the potential difference, one has a potential, the copper electrode has a potential of 0.34 positive, and zinc electrode has a potential of minus 0.76. So zinc has a tendency to get oxidized and copper has a tendency to get reduced. So what is the electrode where reduction occurs? It is the cathode. And what is the electrode at which oxidation occurs? It is the anode. Therefore, out of these, which one will become the anode and which will become the cathode? The copper electrode will become the cathode and the zinc electrode will become the anode when you join these two. You can understand that just on the basis of looking at the values of their EMFs. So we can prepare a Daniell cell, and the half reactions would be the left electrode, that is the anode, would be zinc electrode where oxidation will occur. So zinc ions will, from zinc metal 2 electrons will be lost and zinc ions will enter the solution. And on the right hand side, the copper ions which are present in the solution will gain 2 electrons which travel through the external circuit, and it will turn into copper metal solid which will get deposited. And that is what we did in the previous video. The overall reaction is zinc plus copper ions in the salt solution will give you zinc ions plus copper solid. So zinc gets oxidized, copper gets reduced. And how would you calculate the EMF of this cell now? We know the EMFs of the half cells already from a table that is given to us. For all electrodes, all metals and most of the elements which can be used to prepare the half cells or the electrodes, a series has been created. And this series of elements gives us the EMF of all of them as they act as electrodes. So on the basis of their values, you know which one is anode, which one is cathode, and theoretically you can calculate the EMF of the cell. So theoretically, since we have not carried out the reaction here, so let us see what would the electrode potential or the potential difference or the EMF of the cell be. EMF of a cell is calculated as E0 cell, which is E0 R minus E0 L. On the right hand side you have the cathode, and we know that the cathode is copper cathode. So what is its value? What is its EMF? It is 0.34 volts minus E left is anode, and anode has a value of negative, and we subtract it, and when both of these become positive, then so 0.34 volts plus 0.76 volts would be 1.10 volts, and that is the EMF of a Daniell cell. And that is how you calculate the EMF of different cells where you have different electrodes of different metals or different material. Let us now talk about inert electrodes. As we took the standard hydrogen electrode, we took platinum, and sometimes we take even gold, that is noble metals are taken. And these noble metals that themselves do not react, because when you have an electrode which is either a gas or a liquid, it is not possible to have a metallic rod because it's not a solid that is dipping in a solution. So you need a surface which acts as the catalyst, or the surface which provides the platform at which the process occurs. For that, inert electrodes are used. As we saw in the case of hydrogen electrode, platinum is used, and when you have bromine, in the case of a bromine electrode, which is a liquid, you use platinum too. So platinum solid is used for bromine, which is aqueous, and bromide ion is produced. And for this electrode also, an inert for this half cell also, an inert electrode is used. In the case of this bromine reaction where platinum is used as the electrode, or as the inert electrode, the half cell reaction would be half molecule or half mole of bromine molecules in the aqueous solution would gain an electron to give you bromide ion, that is the ion in the solution. Now, with that we understand why we took the inert electrode and how we have a series of electrode potentials, and just by looking at that table, if you were asked to create a cell and calculate its EMF, you would be able to do it. If the electrode potential of a half cell is positive or is greater than 0, that signifies that the reduced form is more stable. Now I'm revising this because this is really important to understand. That if the value of electrode potential is positive, it means that it is the reduction potential, it has a stronger tendency to remain reduced. And therefore, this substance would act as an oxidizing agent, as was the case of copper. In copper, the value was positive 0.34 volts. And therefore, its reduced form was more stable and it had a tendency to act as an oxidizing agent in comparison to any other member in that series which has a value that is lower than 0.34 volts. So, in this entire series, you may have two electrodes which both of them have positive values. Then in comparison to each other, which one is more positive and which is less positive, that will decide the electrode, the EMF of the cell, and which is going to get oxidized and which is getting reduced, because ultimately it is only a comparison, it is only a tug of war. The stronger oxidizing agent, or the substance that has a stronger tendency to get reduced, always wins, and that causes the difference in the electrode potential. So if you look at this entire series, we notice that fluorine is right on top of the series and lithium is right on the bottom. So fluorine is that element which has the strongest tendency to act as an oxidizing agent or to remain reduced. It has a strong tendency to get reduced, and lithium, being at the bottom, having the most negative value, has a strong tendency to get oxidized and a very low tendency to be reduced. So this was the measurement of electrode potential, and with this I'll finish this video. If you found it helpful, give me a thumbs up, I would appreciate that. Subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.